here. Okay, so so we are at lecture 3. So let me start by doing a quick recall of what we have been doing. So in the first lecture, we have seen an introduction to the world of synthetic curvature lower bounds and the definition of CDKN spaces. So the CDKN spaces, they are yet to think. So one should think of them as kind of possibly non-smooth synthetic Finsler-like structures with lower bound on the Ricci by K and upper bound on the dimension of n. K and n are two real parameters. K is any real, and n goes from 1 to plus infinity. So plus infinity is also allowed, and it means that you are basically assuming no upper bound on the dimension. These kind of spaces include all the Ricci limits and include also Finsler manifolds. Then we saw that Finsler manifolds do not appear as Ricci limits. There are some theorems that we would like to be able to prove in the static setting, which are not true in the Finsler setting, like the splitting theorem. And so we saw this refinement of the Riemannian CDKN spaces, which one has to think of them as kind of non-smooth Riemannian-like structures with lower bound on the Ricci by K and upper bound on the dimension by n. We have seen that there are two slight variations of this notion, the RCD and the RCD star. They agree on spaces of finite measure, but in general, for a space of not finite measure, it may happen, we think not, but it may happen a priori that the RCD star condition is more general than the RCD. Okay, then we have seen that actually in the RCD star condition, actually there is from the point of view of the axiomatization, a priori there may be some difference in the non-finite measure case, but from the point of view of say properties and applications, actually RC star is all the known inequalities are in sharp form in the RC star condition, and in the RC star condition we have equivalence with the dimensional Bochner inequality. And then we have seen also that the RCD and RC star are both stable under pointed measure Gromov convergence. Point measure convergence is weaker than pointed measure Gromov-Hausdorff, and so a priori, and so in particular, all the Ricci limits are in the class of RCD KN spaces. Again, so what is this RCD? It means that you are assuming CD or RCD star plus the infinitesimal libertianity, which means that the Cheeger energy is a quadratic form on its domain contained in L2. Okay, so this is a brief recap of what we did in the first two lectures. So what is the goal of this lecture? So the goal of this lecture is to give you an account of the structure theory of RC star KN spaces for finite n. So let me stress here that today I'm considering only the case when n is finite. So these are non-smooth spaces of finite dimension, and they are Hausdorff dimensions above by n. And we are going to see that basically all the deep and beautiful structure theory for Ricci limits that has been developed by Cheeger-Colding, Cheeger-Naber, Colding-Naber, etc., holds also for RCD. This is not trivial at all, because as we have seen in the second lecture, the class of RCD star KN spaces strictly contains Ricci limits. So even if one has the feeling that a theorem could be true for RCD, then you have to prove it from scratch in the synthetic setting, and the proof must be quite different, because how the proofs usually work in the Ricci limit case is that one proves estimates for smooth manifold with lower bound on the Ricci. Such estimate must be, say, quantitative and strong enough to pass it to the limit, and then one pass this estimate to the limit under pointed measure of Hausdorff and obtain estimates on the Ricci limits and infer, and one infers structural properties. In the RCD setting, there is no smooth approximating sequence, and so one has to work directly on the no-smooth space, and this needs new proofs, basically. Okay, but we're going to see, let's say, the structure theory at the level, so for RCD is basically apart few results, but say the bigger, say most of the structural theory for the Ricci limits goes to the RCD setting. Okay, so this is what we are going to do today. And instead, the lecture of tomorrow will be about sharp and rigid geometric and functional inequalities, and we are going to see that also some applications to the smooth setting, so to smooth Riemannian manifolds. Okay, maybe just one other thing about lecture 3. So we've seen, say, for the for the structure theory of RCD, of course, since Ricci limits are contained in RCD, as I was saying, if you want to prove something in RCD, you need some new proof from Ricci limits. But on the contrary, if instead you have some conjecture that you may think it could be true for RCD, but you disprove it for Ricci limit, then of course you disprove it also for RCD class because it is larger. Okay, and we're going to see an example of this behavior in the last part of this talk. Okay. Any question about this recap before I start with the structure theory? Okay, now, so let's start with the structure theory. So a basic tool in order to infer structure is the splitting theorem. So this is a key theorem already for smooth manifolds. This is due to Cheeger and Gromov in 1971, who proved that given Mg, a complete and smooth Riemannian manifold with non-negative Ricci, if such a manifold contains a line, so what is a line? A line is an isometric immersion of the real line. Then the manifold M splits isometrically a factor R. So M is isometric to M prime times R, where M prime is a smooth manifold with the Ricci non-negative. Okay, so this is a superclassical result, which actually generalized to Ricci lower bound a previous result by, I think, Gromov, who proved first that one has a splitting for non-negative sectional curvature. Okay, so another statement generalized to Ricci limits by Cheeger-Colding. So they proved that also Ricci limits split. And it was generalized to the even more general setting of RCD star 0 and spaces by Gigli. So the statement in the RCD setting is as follows. So consider an RCD star 0 and space, XDM. Assume that X contains a line. Then there exists an RCD star 0 n minus 1 space, X prime, with metric D prime and measure M prime, such that the metric measure space XDM is isomorphic as a metric measure space to the product X prime times R, D prime times the Euclidean metric on R, and M prime, which is the measure over X prime, tensor product with the Lebesgue measure over R. So you have a splitting as a metric measure space. So all the structure, the distance, and the measure split isomorphically, I would say. Okay, so you have really the exact same statement in the no-smooth setting, which is very powerful. Okay, now in their beautiful paper in 1997, Cheeger and Colding proved that for Ricci limits, the local blow-ups are almost everywhere unique and Euclidean. So what do I mean with blow-ups? I mean that at every point, at almost every point in your Ricci limit, so remember that the Ricci limit may be non-smooth. So we already discussed examples of a cone or points or a Ricci limit where the set of conical points is dense. Okay, so you don't expect your Ricci limit to be smooth, but you may hope that most of the points, in the sense of measure, are regular in the sense that they admit a tangent space which is unique and Euclidean. And what is the right way to phrase these tangent spaces is you go in to a point, you start rescaling your space, you do what is called the blow up. By Gromov compactness theorem, this sequence of blow-ups will admit a subsequence which converges, and you would like to know, and you would like to prove that all the limits that you obtain by rescaling are a Euclidean space of the same dimension. This is your goal and what you would like to obtain. Okay, so this is true actually for Ricci limits, and the question is it true also for RC spaces? So yeah, let me fix some notation, making more precise what I just said in words. So we fix x bar, a given point in our space X, and we call tan xdm x bar the set of local blow-ups, which are also called tangent cones of X at x bar. Let me mention that this word tangent cone is standard in the field, but can be a bit misleading because these tangent spaces may not be cones. Okay, so they are just metric measure spaces which are obtained by applying Gromov compactness theorem. So you are rescaling your space, and in the limit you obtain a metric measure space which by stability will be an RCD 0 in space, but a priori it doesn't have a conical structure. Maybe the name comes by the fact that in the non-collapsed case of Ricci limits, the tangent cones are metric cones, and so one can think of them as tangent. So they are really tangent cones. But in the collapsed case, so when you've loss of dimension in the limit of the Ricci limit sequence, the tangent spaces, there are actually an example that tangent spaces may not be even polar spaces, so they are not tangent cones in general. So they are not cones in general. Okay, just close parentheses. Okay, so what about existent? What about almost everywhere regularity of the RCD spaces? Okay, so together with Gigli and Rayala, we prove the following statement, which is saying that at almost every point there exists at least one Euclidean tangent space. Okay, so we are not claiming uniqueness. We are just saying that that almost every point admits a sequence of blow-ups which is converging to a Euclidean tangent, to a Euclidean space. Okay, so the precise statement is that if you are given xdm an RCD star k in space, then for almost every point, for almost every x in X, there exists some n integer number which may depend on X, which is bounded above by the big N, which is the big N coming in the RC star condition, such that R small n with Euclidean metric and Euclidean measure is a tangent, is a blow up at X. So is one of the possible tangent spaces or tangent cones, if you will.
There's a question in the chat.
Yeah. Okay, is it a set because we might have different limits depending on how we may take blow up? Yes, yeah, that's a very good question. Thank you, Andrea. Yes, indeed, tan. Exactly. So the answer is yes, because if you have a unique tangent cone, then tan is just one space. But recall how it is, how tan is constructed. So at every point x, at every point x bar, you consider any possible sequence of rescalings which is going to 0, and you rescale your space. Then by Gromov compactness theorem, you have a subsequence of the spaces which is converging in measure Gromov-Hausdorff, and you call all the possible limit spaces tan. Okay, so a priori you may have more than one blow up. You may have more than one element in tan if and this depends on the geometry. This depends if the geometry of your space X depends on the scale near X bar. And there are examples of Ricci limits even where the space of tangent cones is not given just by one, but by one element. So yeah. So in general, you may have more than one tangent space. But you're going to see that almost everywhere that's not the case. So almost everywhere we're going to see that almost everywhere the tangent cone is unique and is Rn. Okay. Okay, but we start by showing that just that. So in this statement here, I'm just claiming that there exists at least that almost every point admits at least one tangent cone which is Euclidean. Here I'm not claiming uniqueness. Okay, so how does the proof go? Okay, so the starting point is to observe that almost every point X bar in X is the midpoint of some geodesic, and this is a nice argument with optimal transport. So the idea is that you take a point, you take a ball near the point, you consider the optimal transport from the ball to its center. This optimal transport takes place along geodesics. And these geodesics are covering almost all of the ball. You repeat this argument for all the balls, and you show that almost every point is an interior point of some geodesic, and then restricting this geodesic to a smaller piece, this point, almost every point is going to be a midpoint of some geodesic. Okay. So why you do that? Why you're interested in showing that almost every point is a midpoint of a geodesic? Because this geodesic may be very, very short, but now when you start rescaling around this point, X bar, what happens is that you are enlarging your space. So this very short segment of geodesic is becoming larger and larger, and in the limit is going to be a line. So it is going to converge to an isometric immersion of R. Okay. And now what happens to the lower bound on the Ricci? So as it happens in the smooth case, when you rescale your space by R, then the lower bound on the Ricci scales as 1/r². So when you are rescaling by larger and larger scalings, your lower bound on the Ricci is approaching 0. And so in the limit, by the stability of the RCD condition that we have seen yesterday, the limit space, which we obtained by Gromov compactness, is an RCD star 0 n space. Okay, so this limit space, I call it Y. By definition, is an element of tan. Okay, and it will contain a line. Notice that up to here, you can say that every tangent space every tangent space at X bar contains a line. So up to here, really every tangent space. Okay. Now, by the choice of X bar, since it is a midpoint of the geodesic, and this argument, we have that this Y contains a line, and therefore by the splitting theorem, it will split an R factor, and so this Y is going to be Y prime times R. And notice that up to here, you really have that almost every point, that for almost every point, all the tangent spaces split in R factor. Okay. Now, what is the idea? Now you would like to prove that that this Y prime splits in turns another R factor, and you would like to argue by iteration and in order to show that your y is really Rn. Okay, so you want to repeat this argument to y prime. Now, y prime is an RCD 0 n minus 1 space. So again, we repeat the same argument. So we say that almost every point in y prime is the midpoint of some geodesic. And so we get that when we blow up at this point in at this almost every point in y prime, we get a local blow up that I denote with y prime tilde, which splits an R factor. I'm just repeating the same argument at the level of y prime. So this y prime tilde splits an R factor, and so this y prime tilde can be written as y second times R, where y second is an RCD n minus 2, because every time I take one less by the RCD. Okay, and now what we would like to do, we would like to say that this second blow up, so this y prime, this y second times R, then we have still another R coming from the first blow up, which is a blow up over a blow up. Okay, so we took a tangent space, then we took a point in the tangent space, we blow up it there, so we're doing two blow ups. We would like to say that these two blow ups can be realized as just one blow up by choosing a suitable sequence in the original space Y. And this is a very powerful and classical idea by Price, who proved in a quite different setting of measures in Rn that almost every point, tangents of tangents, so blow up over a blow up, are tangents themselves. So you can find if you're iterating twice the blow up, almost everywhere, for almost every base point, you can find a sequence of rescalings in the original space X, which is converging to this second blow up. Okay. So in other words, by applying, so this idea needs need to be implemented in the metric measure setting, because in the paper of Price, it was done for locally measures in Rn, but this can be done. And adapting this idea, you can prove that this y second times R squared is actually a tangent cone of the original space X in X bar. So notice that here what I'm doing is I'm taking the second blow up, y second, I'm doing times R squared, because this is nothing but the blow up over y prime. Okay, now we have done it twice, but now you can imagine that you can do it finitely many times until this number here, which is n minus 2, becomes between 0 and 1. And now when you have an RCD space n0, where n is between 0 and 1, this must be a point. And so in finitely many steps, you conclude that you have a Euclidean blow-up. But notice that here, in order to apply this Price scheme, we lose the uniqueness. We just prove that we can find a rescaling which is converging to the Euclidean tangent space. So with this proof, you prove that for almost every point there exists a Euclidean blow-up, but you don't get uniqueness. Any question about this proof?
Andrea, did you need the first point? Because there is always a local geodesic starting from a point. If the set is not reduced to a point. So it means that
not so you really want to be a midpoint. So for instance, if you have a cone point, so if your point X bar is the tip of the cone, then you have a geodesic where X bar is the final point of your geodesic. But for this, so when you blow up, you just get a half line. But in order to have,
when you make a further blow up, you have a line.
Yeah, but I really need at the first step that you are at the midpoint of a geodesic. Otherwise, it doesn't work. because say if you have a cone point, so take a cone point, so x bar is the tip of a cone, then you blow up once and you get the cone itself, so you don't gain anything.
Okay.
Is it yeah, so I think this is really, so having a midpoint of a geodesic, it is really to so you really have in mind to rule out so you really have a ice cream you have an ice cream cone, and at an ice cream cone this is an invariant under blow up from the tip.
Yeah, the result of price, perhaps we choose for you this point.
Yeah, from the result of price, then you will choose another point. So when you blow up, you take another point, yes, and in the end you are able to split n-1 directions because you didn't split the first one. So you still get okay. So I got what you say. So you say that
there is always
if you're interested just in the almost everywhere. Okay, got it. Yeah. If you say if I am just interested in the almost everywhere at an almost everywhere statement, if I have a cone point, yeah, I just forget it, because then at first blow up I change a base point and I get something else. Yes, but so then I think that you will need in any case 1 in order to do step 3. So maybe you can not use it as a really first step, but you will need it to split an R factor when you do the blow up. So when you implement the argument at the level of y prime, you will need step 1. I think so. In case you okay. So what I want to say is that what you need is that there exists at least one point which is a midpoint of a geodesic, but you say this is trivial because your space is geodesic. Yes, I agree. Yes, so maybe I agree. This may be simplified. Yeah. One is to be a bit careful. Now I don't remember the details of the adaptation of price. So maybe when you adapt price, you need that the space of good points where you have a midpoint of a geodesic. This is almost everywhere. I should check it. But I agree that so maybe there is some room to simplify and to just use the geodesic argument to say that when you do the blow up, so you always find at least one point which is a midpoint of a geodesic. Yeah, thanks for the comment.
There's also a question in the chat.
Yeah. I don't know why. Yes, okay. It's very slow when I want to see the chat. How can the Y space vanish before the nth step? Yeah, for instance, yeah, Andrea asked if how can the Y spaces vanish before the nth step. So for instance, here you can build examples. So for instance, consider an small n smooth Riemannian manifold. You put a weighted measure, and as a weighted space, it is going to be an RCD K big N space. But as a Riemannian manifold, the tangent spaces are small n dimensional with the small n strictly less than big N. Okay, then when you apply this procedure, you will just get the tangent spaces of your Riemannian manifold, which are small n dimension, which are small n dimensional, which is strictly less than big N. Okay, so remember that in these RCD-Kn spaces, this big N is just an upper bound on the Hausdorff dimension, but in the collapsed case, the Hausdorff dimension is really smaller than big N. Okay, so I think that this answers the question. If there is no more question, let's move. Okay, good. Okay, so So this proof gave the existence of Euclidean tangents, but what about their uniqueness? In the Ricci limit case, this was proved by Cheeger-Colding, and for RCD, this was proved in a joint work with Naber. So we proved that consider XDM be an RCD star Kn space, then for almost every point, the tangent cone, so this blow up, is unique and it is Euclidean. What does it mean? It means that for almost every point x, there exists small n x, and this small n is at most equal to big N, such that the Euclidean space of dimension n singleton is the space of tangent cones. So the set of tangent cones is a singleton and is the Euclidean space. And actually, more precisely, we proved a rectifiability result for RCD spaces. So what we prove is that we consider an XDM, an RC star Kn space. Then for every epsilon, there exists a countable collection, R epsilon j. Each one of these R epsilon j is a measurable set. This collection, R epsilon j, is covering X up to a set of measure 0, and such that each one of these R epsilon j is 1 plus epsilon Lipschitz to a measurable subset of a Euclidean space of dimension kj, which may depend on j. And this dimension kj runs between 1 and n, and possibly depends on j a priori. Okay, so you have so if you have done some geometric measure theory, this corresponds to notion of rectifiability of subsets. Here you want to speak of rectifiability of an intrinsic space, of a metric space. And so basically what you're asking is that if you throw away a subset of measure 0, then what remains can be covered with Lipschitz charts with values in Rn. Okay. Now, if X is a Ricci limit space, then both the uniqueness of tangents and rectifiability was proved by Cheeger-Colding, and their proof goes via Hessian estimates on harmonic approximation of distance function. So what they do, they consider distance function from suitably chosen points. They regularize the distance function by taking some harmonic approximation. Then they prove Hessian estimates using Bochner inequality on this harmonic approximation, and they use these Hessian estimates in order to force a splitting behavior. Now, at the time of the joint work with Naber, the notion of Hessian was not still at the same level as for smooth manifolds, and could not be used in such a strength. And so, in order to overcome this difficulty, we proved some new estimates. So we proved some gradient estimates on the excess function and a new almost splitting theorem, which involves the excess. And these two new ingredients allows us to work with distance functions directly without using harmonic approximation. And so we use the distance function itself as chart maps for the Lipschitz maps. And this approach was new also in the smooth context. Now, in the meantime, so after our work appeared, there's been a surge of activity in the RCD community, and in particular in developing calculus tools. And here they mention work of Gigli and Gittamanini, who developed a powerful second-order calculus for RC spaces, in particular a second variation formula along Wasserstein geodesics. Moreover, in the last years, there's been also a great work about stability properties, so about stability properties of first and second order objects, of differentials and of Hessian and Laplacian, proved by Ambrosio and Honda. And so building on top of such more advanced calculus tools, let me mention that Brouet, Semola, and Pasqualetto recently, I think last year or a couple of years ago, gave a proof of the rectifiability of RCD spaces, so of this result that I just mentioned about the rectifiability of RCD star K and spaces, more in the spirit of the original proof by Cheeger-Colding. So with all this calculus machinery, now one is able to mimic the classical arguments by Cheeger-Colding also in the RCD setting, and this was done in a paper by Brouet, Semola, and Pasqualetto, which has been published in the Annales Academia Fisica. Okay, but here let me give the slight different proof in the RCD setting that could be interesting, say, in its own. So the starting point is, as in Cheeger-Colding, to consider the subset AK, which is the space of points X in our space big X, such that there exists a tangent cone of the space at X, which is Euclidean of dimension K, but no tangent cone at the same point splits Rk plus 1. Okay, so this AK are the set of points where, say, the maximal splitting factor is Rk, but you're not splitting Rk plus 1. And more strongly, you are asking that Rk is not just the maximum splitting factor, but the tangent, there exists really one tangent cone which is equal to Rk. Okay, so as a first step, one proved that this AK is M measurable, and this is not hard. It is just a bit technical. You just prove that it is different of analytic sets, and then you observe that since by theorem 1, which is the one about the existence of Euclidean blow-ups, we know that almost every point admits a Euclidean tangent space. You have that almost every point is in one of these AK, because it will have some Euclidean tangent space, and you just take the one of maximal dimension, and it will be in one of these AKs. So by theorem 1, you have that these sets AK are covering all of X up to a set of measure 0. Okay, so now the theorem 2 and 3, so theorem 2 was the uniqueness of tangent cones, and theorem 3 was rectifiability. So it is enough that almost every point in AK is a unique tangent cone equal to Rk, and that AK is rectifiable. Okay, so this is the theorem 4. So let's read it. So XDM is an RC star K, big K, big N space, and let A small k be as above. Then, first claim, almost every point in A small k has unique tangent cone, which is isomorphic to the small k dimensional Euclidean space. And the second claim is that this A small k is small k rectifiable. So that there exists some epsilon bar such that for every epsilon between 0 and epsilon bar, this A small k is small k rectifiable via 1 plus epsilon Lipschitz maps, which means that for each epsilon bigger than 0, we can cover this set A small k up to a set of measure 0 by a countable collection of subsets U small k epsilon, with the property that each one of these sets U epsilon is Lipschitz to a subset of Rk. Let me state that these U epsilon are not open. So these U epsilon are just Borel sets with the Lipschitz maps into a Euclidean space. Okay, so here there's no control on the topology really. It is just a rectifiability result. Okay, so now let me give you any question about the statement before I move to some ideas of the proof. Chat, nothing in chat. Okay, good. Okay, let me give you a rough idea of the proof. So let's start from taking good point from the previous theorem. So we already know that almost every point has a blow up, which is a Euclidean space. So let's consider this X bar, which is in AK. So being in AK is telling us that this X bar admits one tangent cone, which is Euclidean space of dimension K. Okay, so what does it mean that you have a tangent cone of which is Euclidean? It means that you can find a rescaling such that a ball of centered in this point is close in Gromov-Hausdorff sense to a ball in the Euclidean space. Okay, so if you implement with some precision this idea, you have that for every delta small enough, so fix every delta, so fix delta as small as you wish. Then the fact that you have a Euclidean tangent cone, it tells you that there exists a rescaling, so R, such that when you consider the ball of radius delta minus 1 R centered in X bar, this is close to the ball of the same radius in the k-dimensional space. And how you get this? You say I rescale my ball with a factor R, and then I have a ball of radius delta minus 1 in my rescaled space, which must be close to a ball of radius delta minus 1 in the Euclidean space. Okay, so here it is just saying that you rescale your space, and then a ball in the rescale space is closer to a ball of the same radius in Rk. Okay. Now, since you have rescaled, and now you have a big ball in your rescale space, which is close to the ball in Rk. Now the idea is that since you are close to Rk, you consider the standard basis in Rk, and you can find points in your rescale space which are close in Gromov-Hausdorff to these points in the basis of Rk, and I call them Pi, Qi. So this Pi corresponds to the EI vector in the basis of Rk scaled by R, which is a given scale between R and delta minus 1 R. So I'm just taking the standard basis and you rescale it in the appropriate way, and Qi corresponds to minus this vector. So this Pi Qi, you have to think of them as kind of orthogonal points in the rescaled ball in the RCD space. Okay. Now you have in mind to construct a Lipschitz map, so using this point. So how you do that? So the idea is to consider the distance function between these points and center it in X bar. So if you consider the map D vector, which is the distance from the first point P1, and then you just subtract the distance from the point P1 at the point X bar, such that this is 0 at X bar, and then you do it for all the elements of the basis. So you go from P1 up to Pk. Okay, so this gives you a map from the ball of radius R centered in X bar with values in Rk. Okay, now we know by the fact that X bar is in AK, we know that for delta sufficiently small, this map D is an epsilon Gromov-Hausdorff map from BR in the point from the ball of center X bar and radius R in the space with the ball of the same radius centered in Euclidean space. Okay, by the fact that we know that the tangent cone is by the fact that we know that a ball centered in X bar and the radius R is close in Gromov-Hausdorff to Euclidean space, we have that this map D bar is an epsilon Gromov-Hausdorff map. So there is a little bit of check, but that's believable. Okay, but now the main claim is that we can find a subset U epsilon in this ball, which has almost full measure, so meaning that the measure of the ball minus at U epsilon is small, such that the map D is not just a Gromov-Hausdorff map at scale R, but it is a Gromov-Hausdorff map with error epsilon at every scale. Okay, so we say that for every point x in this set U epsilon, and for every s less or equal than R, the restriction map D to this ball with values into Rk is an epsilon Gromov-Hausdorff map at every scale. So notice that when you have the ball of radius s, it is natural to have here that you are an epsilon s Gromov-Hausdorff map. So we want that the Gromov-Hausdorff map is scales as the radius of your ball. Otherwise, when the ball is too small, having an epsilon Gromov-Hausdorff map is going to be meaningless, because you are just saying that you don't see error up to distance bigger than up to a distance less than epsilon, and if s is smaller than epsilon, this is an empty statement. So you, in order to be a meaningful statement, you want that the error scales as the radius of the ball. Okay, so you want to so let me repeat. So you start from a Gromov-Hausdorff map which is a small error at a fixed scale. Okay, and now you want to select a smaller subset U epsilon such that the same map is Gromov-Hausdorff at every scale. Okay, but now the fact that it is Gromov-Hausdorff at every scale tells you that it is actually B-Lipschitz with Lipschitz constant 1 plus epsilon. Okay, this is an exercise. It is not too hard. And now once you have that, you say that every ball have this, every small ball has this set U epsilon, which is good when with just a small error in the measure. Now you cover your set AK with such sets U epsilon, and you get that your AK is rectifiable itself. Okay, so is the strategy clear? Any question about the strategy? Now I'm going to tell you how to prove the main claim. Just a few ideas how to prove the main claim. So the goal is to select a subset such that your map D is epsilon of Hausdorff at every scale. Okay, so how to construct this set U epsilon? So the idea is to consider the excess function. So the excess function between 2 points, PQ. This is classical, so this excess function already appears in the 80s. So this excess function PQ is the distance between P and Y plus distance between Q and Y minus distance between the 2 points. So how to think of the excess function? So notice that if Y lies along a geodesic connecting P and Q, then the excess function is equal to 0, because you have equality along a length minimizing geodesic. So this excess is telling you in a quantified sense how far Y is from being along a geodesic joining P and Q. So and when you want to force splitting, you want to say that every point is along a geodesic because you are splitting. Okay. So in order to get the main claim, we will prove 2 new ingredients. So the first one is a gradient estimate on the excess. So what is classical, and it is no, I don't remember the name, but so what is classical is Ambrosio-Gromov inequality. Got it? So Ambrosio-Gromov is a estimate on the excess function on the excess function, while what we get is an estimate on the gradient of the excess function. So what we prove is that the gradient of the excess function between these points pi, qi. So remember that pi corresponds to ei and qi correspond to minus ei. Okay, so the excess function of these 2 points is small in L2. So more precisely, we prove that for delta that we chose above, which was how close our ball is in Gromov-Hausdorff to Rn. So for delta small enough, we have that the gradient of the excess between pi and qi is small in L2 on the ball of radius r. Okay, so what is the idea? So why this should be true? Well, because in Rn, we have that when we take say ei and minus ei, then x bar is along a then 0 is along a geodesic connecting ei and minus ei, and so the excess then the excess is equal to 0, and the gradient of the excess is super small. And here we expect that something like this should be true also in the non-smooth setting by the fact that we are forcing these points to correspond to almost orthogonal points. But the proof is not using that. The proof is using heat flow and estimates, etc. Okay. Then the second ingredient is an almost splitting theorem via excess. So you want to so the idea is that first you infer that the excess is that the gradient of the excess is small, and then you want to bootstrap this information to get that when the gradient of the excess is small, then you are close to a splitting. So that you want to bootstrap these 2 ingredients and get what we want. Okay. So the second ingredient is this almost splitting via excess. So it is saying that given some point x in the ball of center x bar and radius r and a scale s between 0 and small r, if we know that the gradient of the excess is small in L2, in an average sense in the small ball, then this small ball is close in Gromov-Hausdorff sense to a splitting. So this small ball is going to be close at its own scale. So notice it is epsilon times s close to the ball in a splitting space. Okay. So and this is very important because notice that here we have a small ball s. The range of the excess is small on this ball, and then the ball is going to be close at its own scale to a splitting ball. Okay, so so the gradient of the excess is small in L2 is telling you that you are close to a splitting. So it is an almost splitting once you have an estimate on the excess. Okay, and now the idea is to combine these 2 ingredients. Okay, so what do we have in mind? So we have in mind that if we know that the gradient of the excess is small at every scale, so that we can apply this at every scale, then we are going to be close to splitting at every scale. Okay, and this is what we want. Remember that our claim is to show that we can find a set of large measures such that we are close to Rk at every scale. Okay, so how to force that something is small at every scale? And the classical analytical tool is to consider maximal function. So let's consider the maximal function of the gradient of the excess squared. So for a point x, consider the maximal function of the gradient of the excess, which is this is classical in analysis. So you are taking the sup over all the scales, the sup of s running from 0 to r. So you're taking the sup over all the scales of what? Of the sum of all your points. So remember that you have p1, p2, pk. So you have k points. So you are summing up over all of them of what? Of the L2 norm squared of the gradient of the excess, which is what you want to show that it is small. Okay. And now your set U epsilon, the one that you want to show it is close to Rk, is the set of points where the maximal function is less than epsilon, right? Because if the maximal function is less than epsilon, it means that this guy here is less than epsilon. So here you have a soup over all the scales. So it means that every guy is small at every scale. But now by the almost splitting theorem via the excess is telling you that you are close to RK at every scale, which is your claim. Okay. So how to show that this U epsilon is large? So notice that this U epsilon large means that the set where the maximal function is smaller than epsilon is large measure. But this, if you know, say, Marcinkiewicz spaces, is saying that is equivalent to say that the maximal function is small in the space L1 weak. Okay, the Marcinkiewicz space. But now you have that by the continuity of now you have that the maximal function is a continuous operator from L1 to L1 weak. Okay, so in order to have that the maximal function is small in L1 weak, you only need to check that this function here is small in L1. Okay, but small in L1 here means that the gradient of the excess is small in L1 on the big ball. But the fact that the gradient of the excess is small in L1, that the gradient of the excess squared is small in L1 in the big ball is nothing but our first result, which was saying that if we are closing Gromov-Hausdorff to RK, then the gradient of the excess is small in L2, because you have 1 and 2. Okay, so combining these ingredients, you get that for delta small enough, delta was the closeness of the original ball to RK, we have that this set U epsilon is covering a large part of the ball, which is what we wanted. Okay, because now you say that now, yeah, I'm just repeating what I said in words. So now collecting everything, we get it for every point X in U epsilon, and for every scale less than R. By construction, we have that the sum of the average of the gradient of the excess squared is less than epsilon. This is just the definition of U epsilon and the definition of the maximal function. But now, in iteration of the almost splitting theorem via excess, it's telling you that you are splitting first, that you are close to splitting of U1 between P1 and Q1. Then you're splitting P2 and Q2 and so on. So you iterate it k times, and it's telling you that the Gromov-Hausdorff distance between the BS ball in X and the BS ball in RK is smaller than epsilon times S. So it is epsilon small at its round scale, which is giving the claim, which was the B-Lipschitz, that D is B-Lipschitz. Okay, so here there are this is not really the proof, so there are some subtleties, because here I just checked that you are Gromov-Hausdorff closer. In order to read the proof to be complete, you need to prove that your map D is the map which is giving you the Gromov-Hausdorff equivalence. So the D is the Gromov-Hausdorff map doing everything. This is a little bit more work, but I just wanted to give you a kind of what are the key steps in the proof. Any question about that before I move to the next? The chat? No. Okay. So this is are some ideas about how to prove the rectifiability as a metric space. So you have B-Lipschitz maps into RK. And so from the last theorem, theorem 4, we know that each set AK, so remember that AK are the set of points where which admit a Euclidean tangent cone, which is RK, and they do not split Rk plus 1. Okay, and we show that this is rectifiable in Rk. But it doesn't say, but this result, it is controlling well the distance, the metric, but it's not saying much about the measure induced over Rk. So is it true that one expect that the measure m induced on each stratum Ak to be absolutely continuous with respect to the k-dimensional Hausdorff measure? Is it true? This is true in the Ricci limit case. This was proved by Cheeger-Colding using estimates. It is not so easy to do the same proof in the RCD case, and so one has to do something different. And this was proved independently by different teams. So by Kelly and myself, by De Filippis, Marchese and Rindler, and by Gigli Pasqualetto, that the measure restricted to each stratum AK is absolutely continuous with respect to HK. So these results, so we posted, then after a couple of weeks it appears the De Filippis, and then after a couple of more weeks it appears the Gigli Pasqualetto, and they all are a bit different from each other, so they are not exactly the same, but the key idea is the same for all the three approaches, and the key idea for all the proofs is to use a result by De Filippis and Rindler, which was previously announced by Cisornei and Jones, which is called converse of Rademacher theorem. So Rademacher theorem tells you that if you have a Lipschitz function in Rk, then it is differentiable almost everywhere. So in particular, if you have a measure, if you have a Radon measure in Rk, which is absolutely continuous with respect to the Lebesgue measure, then a Lipschitz map is differentiable almost everywhere. Now, the converse, Rademacher theorem, asks you the converse implication. So if you have a Radon measure over Rk, and you know that every Lipschitz map with values into R is differentiable almost everywhere with respect to that measure, is it true that that measure is absolutely continuous with respect to the Lebesgue measure? This is a deep problem in measure theory, and the answer is yes. And it was a result of a work about quite different things by De Filippis and Rindler in the annals about harmonic analysis and this A3 PD. So they are studying first order PDs, and it's a beautiful paper which had a lot of applications. Okay, so what the converse of Rademacher theorem says, it tells that let mu be a non-negative Radon measure in Rn, such that every Lipschitz function is differentiable mu almost everywhere. Okay, then this measure mu is absolutely continuous with respect to the Lebesgue measure. Okay, so in order to prove our theorem here, it is enough. So there's some work to do, but it is enough to show that when you consider the projection, so you have your map M, you have your measure M, you have your Lipschitz maps with values into Rk. So if you are able to show that the push forward of M via these maps is absolutely continuous with respect to Lebesgue, then since Lipschitz maps preserve the Hausdorff measure, you will be able to say that the measure M over AK is absolutely continuous with respect to the k-dimensional Hausdorff measure. So you want to prove that the push forward with these Lipschitz maps of M is absolutely continuous with respect to Lebesgue. So what all these three teams did is to prove that the converse of Rademacher theorem holds for the push forward of the measure. So you want to prove that when you push forward m via this Lipschitz map, and then you consider any Lipschitz function on this image, you want to show that any Lipschitz map is differentiable almost everywhere with respect to this measure, with respect to the push forward measure. Okay, and it is done in different ways among between these three teams. Okay. Okay, so this so after this we have that an RCD star Kn space is rectifiable as a metric measure space. So you throw away a subset of measure 0, then what remains can be covered with Lipschitz maps with values into Rk, and the measure restricted to each of these stratum is absolutely continuous with respect to the k-dimensional Hausdorff measure. Okay, and now the question that was around for some time is it true that you may have more than one stratum? So you may have strata of different dimensions. So this was okay, what I say here. So yeah, this is what I say. So the combined result above, X is the union of the strata AK, and each AK is rectifiable with the measure absolutely continuous with respect to HK. Now, is the dimension well defined? So can we have more than one dimension in the strata? So this was an open question already for Ricci limits, because so this rectifiability was already established in Cheeger-Colding, but the fact that the dimension of the tangent spaces may vary along points was an open question after Cheeger-Colding work. And for Ricci limits, the fact that the dimension does not change from point to point was answered by a beautiful paper, quite hard actually, quite technical, by Colding and Naber in the Annals, who proved a beautiful continuity result for tangent cones, which as a corollary gives the uniqueness of the dimension of the tangents. So what they prove, so what Colding and Naber prove, is that if you consider a geodesic in the Ricci limit space, okay, and you consider tangent cones along such a geodesic, then in the interior of such a geodesic, so you have to go a little bit inside from the endpoints, because near the endpoints you may have things can degenerate, but if you stay a little bit inside of the geodesic, then the tangent cones vary in a further continuous way with respect to the Gromov-Hausdorff topology. Okay, so in particular, since they are continuous, they cannot jump from R2 to R3. So they cannot jump from one RK towards some RK prime. Okay, and then by covering argument, you can prove that the dimension of tangent cones is then the dimension of the Euclidean tangent spaces is the same at almost every point. Okay, so you cannot find two sets of positive measure where in one set you have a stratum of dimension 2 and another stratum of dimension 3. Okay, and so they set up the existence of a well-defined dimension, which is if XDM is a Ricci limit, then there exists some k in n such that the measure of X minus the k-dimensional stratum is equal to 0. So the k-dimensional stratum is covering all X up to a set of measure 0. Okay, so all the regular set is k-dimensional, and the rest is the singular set. Okay. What happens in the RCD star Kn setting? So this result by Colding and Naber was in 2012. So it was expected to be true also for RCD, and several people tried, including me, and it was quite hard to they are proof of Colding number in several steps. Was hard to implement. And so two brilliant PhD students from Scuola Normale, Bruet and Semola, managed to arrive with the right idea to overcome this difficulty, and they proved it in a quite different way from Colding and number, the statement that you have a constancy of dimension of RCD. So what they prove is that if XDM is an RCD star Kn space, then there exists some K, some natural number between 1 and the integer part of n, such that this K-dimensional stratum is covering all X up to a set of measure 0. So let me mention some similarities and differences with Colding and number. So Colding and number proved estimates on the smooth approximation, so on a smooth manifold with the Ricci bounded below, and then they proved that the estimates which are strong enough to be stable under passage to the limit in the Ricci limit space, and so they can infer something in the Ricci limit. Now, for RCD, there is no smooth approximation in sequence, and so one needs to work directly on the no-smooth space. Okay. Now, another difference that Colding and number look at how the geometry varies along a minimal geodesic connecting two points, while Bruet and Semola look at how the geometry varies along a versatile geodesic. Okay, so you are the idea here is that you are in a singular space, so just one geodesic may be too little to look at. So you want to look at the regularity in a more averaged way. So you want to consider a versatile geodesic, which is concentrated. So versatile geodesic is concentrated over a family of geodesics, and you can expect that as a family, the geodesics behave better than just one single geodesic, because you have some average given by the measure. Okay. And then another key difference is that Bruet and Semola avoid using second-order differentiation formula, which was key in Colding number, and they obtain some quantitative estimates on flows that I'm going to say in a moment, which are new even in the smooth setting. So their idea is to consider gradient flows, is to consider flows by vector fields and prove estimates, very sharp estimates and beautiful estimates, which are new even in the smooth setting of smooth Riemannian manifolds. Okay, so let me give you some heuristic of Bruet and Semola approach. So the starting point is a basic fact that we all know, but that it is exploited in a clever way later. So if you have a smooth connected differentiable manifold, then we know that given 2 points, x and y in M, we can find a smooth diffeomorphism phi from M to M, which is mapping x into y. Okay. And the fact that you have such a smooth diffeomorphism is telling you that the geometry, the infinitesimal behavior near x is the same as the infinitesimal behavior near y. So in particular, it is telling you that the local dimension near x is equal to local dimension near y. Okay. But this would be the goal in the RC setting, because if you're able to say that for an RC space, then you would say that the tangent cone near x has the same dimension of tangent cone near y. Okay. Now the strategy that will be implemented later is to build such a diffeomorphism phi as a flow map at a shootable time of a shootably regular vector field. Okay, so the fact that you have a diffeomorphism phi is kind of trivial, but the strategy that will be implemented for RCD is to build explicitly such a diffeomorphism phi as a flow map of some vector field. Okay, now the output of the strategy is not new from a qualitative point of view, because from the qualitative point of view, we already know that the dimension on a smooth manifold doesn't change. but it will give you some new quantitative estimates along points which are far away on a smooth manifold. And this is in very much the same spirit of Colding and Naber paper. But if you're able to implement such a strategy in a non-smooth setting, then the result is going to be new also at a qualitative level. So qualitative means that not just at the level of estimates, but at the level of qualitative picture of your RC space. And it is indeed the constancy of the dimension of RC star Kn spaces. Okay, now let me give you a rough strategy of Brouet and Semola approach. So I will skip all the, say, technical statements. I will just want to give some rough idea of what are some of the key steps in the proof. So the first step is to find, so since we want to consider flow maps, we need to find a rich enough class of vector fields which admits regular enough gradient flows, because this phi will be a gradient flow, will be a flow. So forget about gradient. So it will be a flow of a vector field, and we need it to be regular enough. Now, what are vector fields in this setting? The point of view which is relevant here is the sense of derivations in the sense of Weaver, and the flow of a vector field in this setting is in this mathematical setting is the sense of regular Lagrangian flow, and this was implemented in the Euclidean setting by the Pernal ions and developed greatly by Ambrosio in 2004, and then it was implemented in the metric measure setting by Ambrosio and Trevisan in 2014. So the outcome here is that you can make sense of vector fields using derivation in the sense of Weaver. Let me also mention a paper by Gigli in 2018, something like that, who developed vector fields and Hessian in the sense of RCD. And then once you have the vector fields, you can flow them using the notion of regular Lagrangian flow once you have that the vector field is regular enough. So you need some control on this, on his symmetric covariant derivative and some good bounds. But you can do it, and you have time. Then a key step is to investigate the regularity of such flows by vector fields. And Brouet and Semola, a key estimate in their paper is that they are able to establish a very powerful Lewis-Lipschitz regularity property of the flow map. And this is inspired by previous work by Kripp-Ellis in the Euclidean setting, but the proof of Brouet-Semola is really quite different. So so the statement is inspired by, but the proof of Brouet-Semola is really something new. And basically, what does it mean losing Lipschitz regularity? It means that the flow is Lipschitz outside of a set of small measure. So you throw away a set of small measure, and the flow map is Lipschitz on what remains. Okay, and how they get this estimate? So a beautiful idea that they have is to prove the estimate instead of proving the estimate in terms of the distance function. So usually when you want to prove Lipschitz continuity, you use the distance function to prove that the distance is controlled with the distance in the beginning. If you try to do that with these flows, controlling the distance function is not so easy. So what they have is that instead of controlling the distance function, they control 1 over the green function. So they consider the green function of the Laplacian. They consider 1 over the green function. They call it dg. They observe that dg behaves quite like a distance function. And then they prove this Lewis-Lipschitz property with respect to dg. Okay, and this is really a beautiful idea. They measure that it can be thought to be inspired slightly by some previous work by Colding in ACTA, where he proves estimates on the inverse of the green function, but the implementation in this setting is really something new, and it's a beautiful idea that they had. Okay. Then, using such a Lewis-Lipschitz property of the flow map, they prove some very powerful rigidity statement. And roughly, the idea is that if you are using Lipschitz, then on a set of large measure, you are Lipschitz. And so, by considering the map and its inverse, you cannot have a jump in the dimension. So you cannot map a piece of RK1 into a piece of RK2 if K1 is different than K2. This is because Lipschitz map preserve the dimension. So actually, this is just a rough idea. So to the right implementation uses so they kind of are inspired by Sard and by Sard theorem, and they prove some very precise rigidity statement, but this is the rough idea. And now you combine all these ingredients to prove the constancy of the dimension. So the idea is that you start from some point, you take an absolutely continuous measure concentrated in the regular set around one point, and another measure concentrated around another point in possibly a regular set of a different dimension. You construct a Weierstein geodesic between these two. You see this as a flow map of a vector field. Then you show that this gradient flow is using Lipschitz, and so it cannot you cannot have a change of dimension, and so these 2 points, so and so you cannot have this jump in the dimension of 2 regular sets. Okay, so actually the proof is quite complicated and quite long, and here I just gave a rough sketch of some of the ideas involved. Okay, so this is about constancy of the dimension. Now, let me just mention some recent new results about structure. So there's been a beautiful recent paper by Qin Deng, who was able to implement, who was able to prove the Colding and Naber result. So he was able to prove the Hölder continuity of tangent cones along interior of geodesics in RCD star K spaces. But his proof is again inspired, but quite different than Colding and Naber. So Colding and Naber, if you know the proof, their idea is they consider the geodesic, then they do an iteration. So then they consider a tubular neighborhood near this geodesic, and they iterate estimates on the radius of this tubular neighborhood. Okay, and the starting point is a Jacobi field estimate along this geodesic. Now, if you are in a metric measure setting, you don't really have Jacobi estimates along geodesics, and so Deng, instead of doing an iteration on the size of the tubular neighborhood, what he does is he has this geodesic, and he does an iteration on the T parameter along the geodesic. Okay, so he gets estimate and is able to propagate them along the geodesic in the direction of the evolution of the geodesic itself. So it is inspired, but it's quite different. Okay, and then a conjecture, say, or an open problem which was around in the already for Ricci limits, was that okay, we have a Ricci limit space with a well-defined dimension of tangent spaces, which is the dimension of the regular set, which is the Hausdorff dimension of the regular set. So how this speaks with the Hausdorff dimension of the Ricci limit itself? So is it true that the dimension of the Ricci limit space is at most the one of its regular set? So we already know that the singular set is measure 0. So we expect, so in some sense, the singular set is small in the sense of measure. But is it also small in the sense of Hausdorff dimension? So can it be bigger? Can the dimension of the singular set be bigger than the dimension of the regular set? And I would say that quite surprisingly, Wei and Pan gave some examples of Ricci limit spaces where this can happen. So they gave explicit example. This is a very, very fresh paper of maybe less than 1 month ago, where they give some example where the Hausdorff dimension of the singular set exceeds the one of the regular set. So the singular set is of measure 0 with respect to the limit measure, but its Hausdorff dimension is larger than the one of the regular set. Okay, so of course, as I was saying in the beginning, since this is an example for Ricci limits, and Ricci limits are contained in RCD, the same phenomenon happens in RCD. Okay, now in the last few minutes, let me discuss a subclass of the RCD Kane spaces, which will be, I think, next week there will be a talk by Semola who will speak about that. So let me just introduce briefly this class of spaces that will be the object of one full talk next week. So in analogy with the non-collapsed Ricci limit spaces of Cheeger-Colding, so the non-collapsed Ricci limits, remember we said that in the first lecture, you consider a sequence of manifold with lower bound on the Ricci and of dimension n, such that the volume of a ball of radius 1 is not going to 0. Then in this case, the limit space has the same dimension as the approximating sequence. Okay. And then you can and then what they prove, Cheeger-Colding prove, is that the limit space, that the measure Gromov-Hausdorff limit, this limit space, is naturally endowed with the Hausdorff measure. Okay, so in analogy with this theory of Cheeger-Colding, it is natural to consider also a subclass of the RC star Kane spaces, which are the one of where the Hausdorff dimension is equal to n. Okay. And Honda proved that, at least in Honda proved that in this case, the measure m is a constant multiple of the Hausdorff dimension. So exactly as what happens for Ricci limits. Let me mention that this is Honda proved it in the case where the space is compact. There is no reason to believe that in case of a non-compact space, this doesn't hold. This is a good open problem for people who are listening. And we believe it is true, but adapting the proof seems not to be completely trivial. Okay. Now in this case, so when we have an RCD star Kn space endowed with the Hausdorff measure, then the Bishop-Gromov inequality is much stronger. Indeed, it takes the form of Bishop inequality, and this was observed by Kita-Beppu. So you really have that you really have an upper bound on the measure of the ball with the one in the model space. Here, let me mention just what happens in the case of k equal to 0. So you can bound from above the measure of the ball of radius r with the Euclid with the volume of the Euclidean ball. Okay, then De Filippis and Gigli, after work of Kita-Beppu, studied this class of spaces, the one of endowed with the Hausdorff measure, and they were able to extend results of Cheeger-Colding. So they proved that the singular set is stratified. And they were able to prove to extend the Colding volume convergence to the case of RCD. So let me just recall the statement. So the statement is that you fix k and you fix n, and you fix some radius r. Then consider the collection of all the closed balls of radius r contained in RC star Kn spaces, and keep this collection with the Gromov-Hausdorff distance. Okay. Then consider the map that takes any ball Z in this class of space and gives the n-dimensional Hausdorff measure. Okay. Then the Colding volume convergence tells you that this map is real valued and continuous. And this was extended to RCD spaces by Gigli and by De Filippis and Gigli. Okay. Then another result which was true for which was proved by Cheeger-Naber for Ricci limits was a quantitative stratification for the singular set in the non-collapsed case, and this was extended to the RCD setting by Antonelli, Brouet, and Serra. So this covers some part of the Cheeger-Colding, so of the non-collapsed theory of RCD. Okay, and then a couple of years ago with the Kapovic, we extended another part of Cheeger-Colding results for Ricci limits, which is about the Reifenberg theorem and the topological part of a non-collapsed Ricci limit. So in this paper with the Kapovic, we proved that if you have an n-dimensional RC star K space endowed with the Hausdorff measure Hn, so this is top dimension and with Hausdorff measure, then there exists an open and dense subset M in X of full measure, which is bi-Hölder homeomorphic to a smooth manifold of dimension n. Okay, so you have your non-smooth space, but you have an open dense set which is a topological manifold. Then possibly you may have a boundary part. The boundary of X is defined inductively using tangent cones, and this boundary part has Hausdorff dimension at most n-1. So this second part is kind of new for the Ricci limits, because Ricci limits, so the theory of Cheeger-Colding, they take Gromov-Hausdorff limits of closed manifolds, and in the non-collapsed case, they prove that the limit space has no boundary. Okay, here we have possibly boundary because we start from an RC space which is not a limit of smooth manifolds. And for instance, if you take a convex body, if you take a convex set in Rn, this is an RCD space, and it has boundary, and so you have to work with the boundary for a general RC space. And we can prove that the boundary has Hausdorff dimension at most n-1, as one should expect. And moreover, if you consider X and you take out the boundary part and you take out the open manifold M, what remains is something of Hausdorff dimension at most n-2. Okay, so the picture for an n-dimensional RC space is that such an X is this joint union of a manifold part of dimension n, so which topologically is very nice, so it is a topological manifold. Then you have a boundary part, okay, which is Hausdorff dimension at most n-1, and then you have a singular set which is in the interior, which has a Hausdorff dimension at most n-2. Okay, and then we pose some questions about the boundary. And then last year there was a breakthrough paper, I would say, by Brouet, Naber, and Semola, who proved some really strong theorem about the boundary. So they were able to prove that the boundary, as we defined here, is n-1 rectifiable. Okay, this is already something very remarkable. But what is really breakthrough is that they were able to prove that the boundary is also homeomorphic to a smooth n-1 dimensional manifold out from a set of Hausdorff dimension at most n-2. And let me say that in order to prove that this homomorphic for the boundary, they have to prove some new Reifenberg type theorem for in case of boundary, which goes much beyond the Reffenberg theorem of Cheeger-Colding in the interior, that which is what we used in the paper with Kapovic. And this Brouet, Naber, and Semola paper is new even for Ricci limit spaces and smooth setting. So it is really a remarkable paper. Okay. Yeah. Any question?
This is new for Ricci limit space. You mean non-collapse or every?
Non-collapse. Yeah. This is yeah. Both.
No boundary for Ricci limit.
Non-collapse with boundary. Exactly. Yeah.
Ah, okay. So you assume something on the boundary in order to.
Yeah, so you need to assume that that you are concerned. If you want to enter in the RCD setting, you assume that you have a sequence of manifolds with the Ricci negative and which are convex. So you basically you are assuming that the second fundamental form of the boundary is positive, or and actually it is even a bit stronger. You are assuming that that your interior of the manifold is geodesically convex in order to enter in the framework of RCD. But this is new, so this was complete. This was not studied before.
Okay, thank you.
Okay, so then I prepared a lot of slides, but I will have to skip them about group actions. I was a bit optimistic on how quick I could go. And so let me just finish by a summary of RCD. So what we've seen is that some good properties of the RCD spaces. So we've seen that they are stable under convergence. They have some nice equivalency, nice equivalent with gradient flows. They are equivalent to the Bochner inequality. Once you have equivalence with Bochner inequality, one gets good estimates on the heat flow, one gets the Liao inequalities. RCD implies the Cheeger-Gromov splitting theorem. You have a quite strong local structure, which now is comparable with the local structure of Ricci limits, and as we've seen, it goes even a little bit beyond in some statements. One is a good control of the isometries. The isometries are a Lie group. This part I didn't have time to cover, but let me also mention that since it can be useful for applications. If you have an RCD Starkian space, you have a universal cover, and the universal cover is still an RCD Starkian space. And now you can use the geometric control of the universal cover to infer some classical theorems on the what is called the revised fundamental group, which is the space of deck transformations, because there is this kind of principle that the geometry of the universal cover is very much connected to the universal group, to the fundamental group. And then one has the local to global property for RCD and RCD star. Okay, so these are good properties of the. These are some of the good properties. Actually, there are. I could do 3 slides just of mentioning good properties. And then we have seen examples of RCD spaces. So we have seen that Ricci limits, no matter if they are collapsed or not, they are RCD. Alexandrov spaces of finite dimension, and all with the Hausdorff measure. Weighted Riemannian manifolds with the Bark-Emery Ricci bounded below, they are RCD. Cones or spherical suspensions over RCD n-1n are RCD. Then RCD condition is stable under taking quotients, orbifold, and multi-measure foliations. And the setting, which is very interesting, of stratified spaces enters in the framework of RCD spaces. And so you have a good list of examples entering into this class. So the conclusion is that in doing Riemann geometry, one naturally encounters non-smooth spaces, and one encounters non-smooth spaces when taking limits of Riemann manifolds, and we take limits often when you do contradiction argument, blow-up arguments, singularities in geometric flows. Then one encounters singularities also when taking quotients, when taking cones, and when taking foliations of Riemann manifolds, if so, in general. So the message that I was already mentioning yesterday is that if the smooth spaces we started with have lower bound on the Ricci curvature, then the non-smooth space which arise are RCD. Okay, and so you can apply all the machinery that has been developed in the last 10-15 years of this setting. So this class of RCD Starkian spaces can be seen as an extension of the classical setting of smooth Riemann manifold with lower bound on the Ricci, but the big advantage of this RCD class is that it is closed under many natural geometric and analytic operations like taking limits, taking quotient, taking cones, taking foliation, and so on. And this is and this makes this class quite useful. And this is exactly what happens for Alexander spaces. So if you replace Ricci with sectional, instead of RCD, you get Alexandrov, and the Alexander spaces as being super useful in studying even smooth manifold with lower bound on the sectional curvature. And the key properties of Alexander spaces was that they were stable under limits, they were stable under quotients, cone, and foliations, and so one could use the hard part of Alexander geometry as a black box in the smooth setting. And the hope is that all the effort that has been done in the RCD to develop this theory of RCD can be useful also for people who are not interested in developing, say, new tools in RCD. They're interested in doing a smooth Riemann geometry, but they encounter singularities, and then they can just apply as black box all this machinery when it turns out to be useful. Okay, and tomorrow we're going to do some applications, but we expect and we hope that there will be much more. Okay, so I'm already quite over time, so thank you very much for your attention.
Thank you, Andrea. Is there a question? No question. So thank you again, and
Thank you.
See you tomorrow.
Thank you. See you tomorrow. Yeah. Bye-bye. Have a good day.